4 billion miles from where you're sitting right now, something is glowing that has no right to glow. It sits on a frozen rock most people were taught to stop calling a planet. A world so cold that its air falls out of the sky and freezes solid under the ground. Every single year. A world so far from the sun that daylight there is roughly 1/1000th as bright as daylight on Earth. And yet, for the first time in history, humanity's most powerful telescope has looked directly at it and found a signal in the light that scientists cannot yet explain. Not haven't gotten around to explaining, cannot explain, not with any known chemical, not with any known compound in any laboratory on Earth. This is not science fiction. This is a real measurement taken by a real spacecraft, published in real peer-reviewed journals. And it's forcing scientists to ask a question they did not expect to be asking about Pluto in the 2020s. What exactly is this world made of? This is the story of how the James Webb Space Telescope finally turned its gaze toward Pluto, and how, instead of settling old questions, it opened up entirely new ones. Along the way, we'll be careful about something. Most space content online is not. We're going to tell you exactly what has been confirmed by scientists and exactly what is still just a theory. Because the true story here doesn't need exaggeration. It's strange enough on its own. Let's go to the edge of the solar system. To understand why scientists are stunned today, you have to go back 11 years, to the moment humanity first got a good look at Pluto up close. On July 14, 2015, a small NASA spacecraft called New Horizons, after a 9.5-year, 3 billion mile journey, screamed past Pluto at over 30,000 miles an hour, coming within about 7,800 miles of the surface. It had one shot, one flyby, no second chances, no orbit, no do-overs. Just a matter of hours to gather as much data as possible before Pluto shrank back into the darkness behind it. What it found broke almost every assumption scientists had going in. For decades, Pluto had been imagined as a dead, static snowball, an ancient leftover from the solar system's formation, frozen in time, geologically silent. New Horizons proved that picture almost completely wrong. It photographed towering water ice mountains taller than the Rockies. It found vast, smooth plains of nitrogen and methane ice, one shaped famously like a heart, that appeared to be geologically young, meaning something on Pluto is still resurfacing the ground, possibly even today. It found what looked like ice, volcanoes, evidence of glaciers made of frozen nitrogen flowing slowly across the landscape the way glaciers flow on Earth, just built from different ice. And then there was the haze. As New Horizons looked back at Pluto with the sun behind it, a classic trick photographers use to reveal backlit dust or fog, it captured something nobody predicted. Layer upon layer of thin, blue-tinted haze wrapped around the entire dwarf planet, extending upward more than 300 kilometers, or about 185 miles above the surface. That's higher, relative to Pluto's tiny size, than almost any atmospheric haze layer anywhere else in the solar system. This is confirmed. It's in the imagery published by NASA and the New Horizons team. Here's where the story gets interesting, because a haze that thick, that high, orbiting a world with barely any atmosphere at all, raised an obvious question. What is this haze actually doing? Is it just a cosmetic feature? A pretty blue fog with no real function? Or is it actively shaping Pluto's climate? In 2017, a team of planetary scientists led by Xi Jiang at the University of California, Santa Cruz proposed a theory. And it's important that we call it that, a theory, because at the time nobody could test it directly. And Zhang's team argued that Pluto's haze wasn't just sitting there. They believed the haze particles were absorbing sunlight during Pluto's brief day and re-radiating that heat as infrared energy at night, acting almost like a global refrigeration system, cooling Pluto's upper atmosphere far more efficiently than gas alone ever could. If true, this would make Pluto's haze a genuine climate engine. A tiny world where fog, not gas, controls the temperature of the sky. It was an elegant idea. It also predicted something very specific and testable. If the haze was doing this, Pluto should glow slightly brighter than expected in mid-infrared light. Wavelengths invisible to human eyes, but exactly the kind of light modern space telescopes are built to detect. The problem was, in 2017, no instrument existed that was sensitive enough and precise enough to actually check. Think about what that means for a moment. A team of scientists builds a detailed physical model of a distant world's atmosphere, runs the numbers, and arrives at a specific, falsifiable prediction. And then has to simply wait, with no way to test it, because the technology required doesn't exist yet. That's not a small gap in astronomy, it's a common one. Mid-infrared observation from Earth's surface is notoriously difficult, because our own atmosphere glows brightly in exactly the wavelengths scientists needed to examine, drowning out the faint signal from a small, cold world billions of miles away. Earlier, space-based infrared telescopes simply didn't combine the resolution and sensitivity required to pull Pluto's whisper of heat apart from Charon's whisper right beside it. There was a second problem, and it had nothing to do with sensitivity. It had to do with geometry. Pluto isn't alone out there. It has 5 known moons, and the largest by far is Charon, itself nearly 200 kilometers across, more than half the diameter of Pluto. Charon orbits so close to Pluto, and the two are so gravitationally locked together that from the distance of Earth, or even Earth's orbit, their infrared glow blurs into a single point of light. You cannot easily tell in the data how much of that warmth is coming from Pluto and how much is coming from Charon. As lead researcher Tanguy Bertrand of the Paris Observatory later described the problem in plain terms. With older instruments, there was simply no way to know what part of the signal came from Charon and what part came from Pluto's haze. 2 vastly different worlds tangled together in the same beam of light. So the theory sat there for years, confirmed nowhere, tested by no one. A prediction, waiting for a telescope that didn't exist yet. The telescope launched on Christmas Day 2021. It would take almost a full year after launch before the James Webb Space Telescope was finally pointed, deliberately and carefully, at the coldest, strangest, most far-flung world humans have ever explored up close. And what it found didn't just confirm a 7-year-old theory, it confirmed it almost immediately. A speed of scientific vindication that, in a field used to decades-long waits, genuinely stunned the researchers involved. We'll take you there right after this. The James Webb Space Telescope does not orbit the Earth. It sits nearly 1.5 million kilometers away at a gravitationally stable point called the second Lagrange point, trailing behind our planet like a silent shadow. Its enormous gold-coated mirror, 6.5 meters across, built from 18 hexagonal segments that folded like origami to fit inside a rocket, was designed for one overwhelming purpose: to capture infrared light too faint, too distant, or too cold for any telescope before it. Pluto is about as good a test of too cold as the solar system offers. Its surface, temperature hovers between roughly 30 and 60 Kelvin. That's colder than minus 350 degrees Fahrenheit. Its upper atmosphere, cooled further by that mysterious haze, drops to around minus 202 degrees Celsius, roughly 30 degrees colder than models using gas alone had predicted. This is a world that barely whispers in infrared light. Webb had to listen for a whisper from over 3 billion miles away and pick that whisper apart from an equally faint whisper coming from Charon, sitting right next door. Webb's mirror is enormous by space telescope standards. 6.5 meters across, built from 18 hexagonal gold-coated segments, each one individually adjustable to nanometer precision, so the whole assembly can act as a single, seamless, light-collecting surface. That size, combined with Webb's position far from the heat and glare of Earth, is what finally gave scientists an instrument capable of resolving 2 faint, closely spaced infrared sources 3 billion miles away. In 2022, Webb's mid-infrared instrument, MIRI for short, was pointed at the Pluto-Charon system and, for the first time in the history of astronomy, resolved the 2 worlds separately in thermal light. Not as one blurred point, 2 distinct signals, 2 distinct thermal fingerprints. This is confirmed, published fact. The results appeared in papers in the journal Nature Astronomy and Astrophysics in the spring of 2025, led by Bertrand's team using instruments at 4 specific infrared wavelengths: 15, 18, 21, and 25 micrometers. Each wavelength captured a light curve, essentially a graph of brightness as Pluto and Charon rotated, revealing how their surfaces and atmospheres heat up and cool down over time. And when the team finally isolated Pluto's signal cleanly from Charon's, the number matched. The extra infrared glow Zhang's team had predicted back in 2017 was there, almost exactly where the models said it would be. As Shizhong himself put it afterward, it is genuinely uncommon in planetary science for a hypothesis to be confirmed this quickly, within less than a decade of being proposed, when many predictions in this field wait a generation or longer for the technology to catch up. The scientists involved described themselves as, in their words, pretty lucky and very excited. What Webb confirmed specifically: Pluto's haze is not a passive decorative layer. It is an active participant in the dwarf planet's climate. It absorbs sunlight or radiates that energy back out as heat, and in doing so, cools Pluto's atmosphere in a way no gas-only model could replicate. Data further suggested the haze itself is built from Titan-like organic particles mixed with hydrocarbon and nitrile ices, chemical cousins of the smog that blankets Saturn's giant moon Titan, formed when sunlight breaks apart nitrogen and methane molecules high in Pluto's thin atmosphere and stitches the fragments back together into something new. Tanguy Bertrand called this dynamic unique in the solar system. There is no other world we know of, anywhere among the sun's planets and moons, where a haze layer this thin plays this large a role in regulating a planet's temperature. Here's why. This matters beyond Pluto itself. Scientists studying the earliest history of Earth have long wondered what our own planet's atmosphere looked like before life existed. Before oxygen, before an ozone layer, when Earth's air may have been dominated by nitrogen, methane, and haze, not unlike what wraps around Pluto and Titan today. If haze can control a planet's temperature balance this dramatically on a world at the edge of the solar system, it raises a serious scientific question. Could a similar haze-driven climate have shaped the surface conditions of the young Earth, potentially even conditions relevant to how life eventually got started? To be clear, this is a research direction, not a settled conclusion. Zhang himself framed it carefully. By studying Pluto's haze and chemistry, scientists might gain new insight into the conditions that made early Earth habitable. Might. Insight. Not proof. This is exactly the kind of claim we want to flag clearly as an open scientific question rather than an established fact. Pluto is not a stand-in for ancient Earth, but its haze physics may offer a rare, real-world laboratory for testing ideas that are otherwise almost impossible to study directly. So, by the middle of 2025, the picture seemed to be coming together, a 7-year-old theory confirmed. A strange, thin blue haze, revealed as a genuine climate regulator, a tantalizing link to the deep history of our own planet's air. Then, scientists went back and looked more closely at the deeper data Webb had already collected, a longer, more detailed spectrum captured in May 2023, and found something that the haze theory never predicted at all. Something that, as of today, still doesn't have a name. In May 2023, Webb's MIRI instrument spent close to 9 hours staring at the Pluto-Cairn system, using its medium-resolution spectrometer to capture an extraordinarily detailed spectrum across a wide band of mid-infrared light, from about 4.9 to 27 micrometers. During that time, Pluto rotated by roughly 21 degrees, giving scientists a high-quality chemical fingerprint of the dwarf planet's atmosphere and surface in a range of infrared light. No instrument had ever explored there before. This data was originally gathered to study Pluto's atmospheric gases, things like the faint traces of ethylene scientists were hunting for, building on measurements from New Horizons back in 2015, and it delivered plenty on that front. But separately, and more recently, researchers doing a fresh analysis of this same rich data set, alongside comparable Webb observations of Saturn's moon Titan, noticed something odd, a dip, a very specific, very narrow absorption feature in the light, sitting at almost exactly 5.113 micrometers. In spectroscopy, this is how scientists identify what things are made of without ever touching them. Every molecule absorbs light at its own particular wavelengths, like a chemical fingerprint. Find the fingerprint in the light, and you can usually name the molecule leaving it. Astronomers have decades of laboratory data cataloging exactly which wavelengths correspond to which compounds: water, methane, carbon monoxide, and thousands of others. The team checked this new feature at 5.113 micrometers against that entire catalog. It's confirmed, and stated directly in their published research, they did not find any previously reported absorption band from any known compound that lines up with this location. This kind of matching exercise sounds simple, but it isn't. It means comparing a real noisy measurement taken from 3 billion miles away against decades of painstaking laboratory work. Scientists here on Earth, freezing candidate compounds down to outer solar system temperatures, shining infrared light through them, and cataloging exactly where each one absorbs. It's slow, exacting science, built one candidate molecule at a time. And when the researchers ran this specific signal through that entire library, nothing fit. That alone would be an interesting scientific footnote. Unidentified features do turn up in spectra from time to time. It's a normal, if uncommon, part of frontier science, and most eventually get matched to a known substance once the right laboratory experiment catches up. What makes this particular case stand out, what pushed it from a footnote into a genuine puzzle, is that scientists found the exact same absorption feature at essentially the same wavelength on Titan. 2 worlds, separated by roughly 1 billion miles with wildly different environments. Titan is a moon of Saturn, wrapped in a thick atmosphere 50 times denser than Earth's at the surface, sculpted by rivers and seas of liquid methane and an active weather cycle. Pluto is a small, airless-feeling, frozen dwarf planet roughly half of Titan's size, with barely any atmospheric pressure at all. About the only significant thing the 2 worlds share is a chemistry built around nitrogen and methane, and yet the same unexplained dip in the same place in the spectrum on both. To confirm the signal was actually coming from the surfaces of these worlds and not simply from a haze or gas layer floating above them, researchers compared the light from the center of each world's visible disk to the light from its edges. If the absorption were caused by gas in the atmosphere, it should appear stronger at the edges, where sunlight has to travel through more gas at an angle to reach the telescope. Instead, on Titan, the researchers found the opposite. The signal was weaker at the edge. This is confirmed evidence from the published study that the absorption is coming from the solid surface of these worlds, not their atmospheres. There is one confirmed difference between the two signals worth pausing on. On Pluto, the dip is roughly 3 times wider than it is on Titan, even though it reaches a similar depth on both worlds, somewhere around 4 to 5% of the light being absorbed. Same fingerprint, different shape. So what could it be? Here, we move fully into the territory of theory. Informed, careful scientific hypothesis, but not yet confirmed fact. Researchers combed through published laboratory spectra of compounds already known to exist in the atmospheres of Titan and Pluto. Things like ethane, ethylene, acetylene, propane, benzene, and hydrogen cyanide. None of them matched. But the search did turn up several plausible candidates worth investigating further. One is benzene, a ring-shaped hydrocarbon, potentially mixed together with some other, still unidentified molecule. Another is a class of compounds called alkenes, along with ketene, and certain complex molecules that form when methanol ice is bombarded by radiation, all of which show absorption bands in roughly the right neighborhood of the spectrum without yet lining up perfectly. As for why Pluto's version of the signal is 3 times wider than Titan's, scientists have a candidate explanation, though, again, this remains a hypothesis, rather than a confirmed answer. Normally for ices, absorption bands tend to widen as temperature increases, but Pluto is colder than Titan. Its surface sits around 30 to 60 Kelvin, compared to Titan's roughly 90 to 95 Kelvin, which means simple temperature differences actually run in the wrong direction to explain what's observed. Something else has to be responsible. The leading idea researchers are exploring involves cosmic rays, high-energy particles from deep space that constantly rain down on every world in the solar system. Because Pluto's atmosphere is so thin compared to Titan's thick blanket of nitrogen and methane, far more of these cosmic ray particles are able to punch through to Pluto's actual surface, penetrating anywhere from several centimeters to tens of centimeters deep, compared to Titan, where a dense atmosphere shields the ground far more. Effectively, the theory holds that this constant irradiation could be physically altering the molecular environment of whatever substance is producing this signal on Pluto, changing its structure enough to broaden the absorption band without changing what molecule it fundamentally is, to be direct about where the science currently stands, until this substance is measured directly in a laboratory under conditions that mimic Titan. And Pluto, and shown to produce this exact absorption at this exact wavelength, it remains, in the language of the researchers themselves, formally unassigned, not identified, not confirmed, a real repeatable measured feature in the data, with no name yet. And that unresolved mystery is exactly where our next act picks up. Let's be honest about what we actually know and what we don't, because that distinction is the whole point of the story. Confirmed. New Horizons revealed, in 2015, that Pluto is a geologically active, chemically rich world wrapped in a towering, multi-layered blue haze. Confirmed. A 2017 theoretical prediction that this haze actively regulates Pluto's climate sat untested for years, blocked by the technical problem of separating Pluto's faint signal from its moon cairns. Confirmed. In 2022, the James Webb Space Telescope's MyARI instrument finally separated those two signals for the first time in history, and confirmed that prediction, revealing Pluto's haze as a genuine, active climate engine built from Titan-like organic particles and ices. Confirmed. A deeper 2023 spectrum from that same telescope revealed an entirely separate mystery, an unidentified absorption signal at 5.1113 micrometers, coming from the actual surfaces of both Pluto and Titan, matching in location but differing in width, and matching no known compound in any laboratory catalog on Earth, and clearly labeled as theory, not fact. The specific molecule responsible for that signal, whether it's some form of benzene, ketene, an alkene, or an irradiated methanol product, remains an open, unproven hypothesis. The idea that cosmic ray bombardment explains why Pluto's version of the signal is wider than Titan's is a promising but unconfirmed explanation. And the broader idea that Pluto's haze physics might illuminate the conditions that helped make early Earth habitable is a serious research direction, not a settled scientific conclusion. Why does any of this matter if so much of it is still unresolved? Because this is what real scientific discovery actually looks like. And it rarely looks like the tidy, complete answers we're used to from documentaries and headlines. It looks like this. A telescope built to peer toward the dawn of the universe, 13 billion light years away, gets pointed instead at a small, cold, nearby world, and finds something genuinely new, sitting right there in our own solar system, that nobody predicted and nobody has fully explained yet. Pluto was demoted from planet status in 2006. In the years since, it's become almost a punchline for that demotion. The world people bring up to make a joke, not to make a discovery. But the data doesn't care about labels, it cares about evidence. And the evidence web is now returning suggests that Pluto is one of the most chemically active, atmospherically strange, and scientifically fertile small worlds we have ever had the ability to study up close. Consider the scale of what had to align just to get us here. A telescope, folded like origami, launched on Christmas Day, and flown to a gravitational parking spot 1.5 million kilometers from Earth. A gold mirror sensitive enough to detect a whisper of heat from a world 3's billion miles away, and precise enough to tell the whisper apart from the whisper of its neighboring moon. 9 hours of careful observation, capturing light that left Pluto's surface, crossed the emptiness of the outer solar system, and arrived at a sunshield the size of a tennis court, cold enough and quiet enough to finally hear it. And what came back wasn't an ending. It was a door swinging open onto a room nobody knew was there. 2 lines of work will eventually settle this mystery, according to the scientists involved. More observation time with Webb, including detailed mapping of exactly where on Titan and Pluto the signal is strongest, which could reveal whether it's tied to specific regions or materials. And laboratory work here on Earth, recreating the extreme cold, low pressure, and radiation environment of the outer solar system, testing candidates, molecules one at a time, until one of them finally produces that exact dip at 5.1 on 13 micrometers. Until then, Pluto keeps it secret. A world we once dismissed as a frozen leftover, a demoted planet, an afterthought at the edge of the map, is instead sitting out there right now, quietly, reflecting sunlight that carries a chemical signature science has not yet learned to read. Somewhere in that thin, cold air, or in the ice beneath it, is a molecule with no name. We know it's there. We know almost exactly where to look for its fingerprint in the light. We just don't yet know what to call it. And maybe that's the real reason this story matters. Not because of what we've already confirmed, remarkable as that is, but because of what it proves about the solar system we thought we already understood. We have not run out of mysteries close to home. We've barely started asking Pluto the right questions. The next time someone tells you the outer solar system is empty, cold, and finished, tell them about the unnamed molecule on Pluto. Tell them the ice is still talking. We just haven't finished learning its language. There's a particular kind of humility built into this story that's worth sitting with. Every instrument used here, New Horizons and now Webb, is a machine built by people who never expected to see this exact result. Zhang's team modeled a haze and waited 7 years to find out if they were right. Bertrand's team spent years untangling 2 overlapping signals from 100 billion miles of empty space. And the moment they finally succeeded, the data handed them a brand new puzzle they hadn't gone looking for at all. That is, in the end, what real exploration looks like. Not a straight line from question to answer, but a chain of hard-won answers, each one quietly opening a door onto the next question. Pluto has already rewritten what we thought a dead world could be. It may be about to rewrite something else entirely, some small piece of the chemistry that connects the coldest, most distant ice in our solar system to the conditions that 4 billion years ago allowed something on our own world to become alive. We don't know yet. Nobody does. That, more than any headline, is the truth of where this story stands today.